Thank you for the intro. Good morning, everybody. It's a pleasure to start the day with you all. And today I'm going to show you what is our plan to bring quantum advantage, or what I call actually computational advantage, in the transition age and be ready for the age of quantum through quantum and quantum-inspired AI solutions. So I'm going to first talk about who we are, and then a little introduction about our approach, and then through two applications for which I talk about our quantum and quantum-inspired AI solutions. For those applications, I try to show you how we try to bridge this gap. First of all, so I'm from the Innovation Hub of Bundesdruckerei, a company with more than 250 years of history, with the main value and goal of building trust, serving citizens, the government, and the society. And the main path that Bundesdruckerei follows, and the products are based on that, are ID systems, cybersecurity, and digitalization solutions. But I mean, the name suggests that we are a federal printing company, and when I tell to people that I'm a quantum computing expert there, everybody just wonders how and why. But if you look at our KPIs, this one is from last year, we had over 1 billion in sales, and almost almost 40% of it is from secure digitalization solution and cybersecurity systems. And naturally, quantum technology will be a layer on top of that, and also for ID systems. It will provide a more secure and more advanced ID solutions in the future, for sure. And now, what is the focus of this topic for in the innovation? So we know that quantum computers were suggested, I don't know, 50 years ago as an idea to solve Schrödinger's equation for physics problems. But it has been taking such a long time to get there, and in the meantime, physicists and chemists have developed so many efficient approaches to solve the same complex problems. And one of them, which is at the heart of our development, is tensor network, and we use it to solve AI problems. And we know that this already can bring in 100 to 1,000 times speed up, while using much less memory, almost 80% in many cases, and oftentimes with higher precision. And it also uses less energy and save a lot of cost. We are also aware of the power of quantum computers, and we know their advantage and their potential to use less energy and the quantum speed up. So we have designed our project in two lines. One is to leverage the power of quantum-inspired methodology to deliver for today, to build products or product-ready prototypes. We also work with application-specific chips like quantum annealer or Gaussian boson sampling or photonic chips. And in order to be ready for the quantum future, we explore the potential of quantum solutions in the NISQ era, or the noisy, now it's beyond NISQ era, for similar use cases, so that we are ready to solve complex problems in the future. And in the meantime, we bring computational advantage and also train the workforce. And by training workforce, I don't mean just quantum engineers. We are a relatively large corporate, and we have all the processes that need to get used to the future, which is quantum. All of the lawyers, purchasing, the communication, it's a big work to work with all the support that we have in the company to be ready for the quantum future. And of course, since we are a state-owned company, this is a way that we support the German government to embody the quantum technology already now. And our main goal is to sustainably do innovation and be ready for a seamless transition into the quantum age. Now I show you two examples of the use cases that we have worked on. One is synthetic data generation. First, I walk you through what we did with quantum-inspired algorithm. So the objective, obviously, is to address data scarcity and privacy constraint, and where we need a more diverse data set for training ML model, AI models. But then, of course, synthetic data are not real data, but as any machine learning models, they are vulnerable to adversary attack. So in order to have like a robust and secure product, we need to have like a layer of privacy protection that in this case, we use differential privacy, so that like any individual's data and contribution to the data set is also safe and indistinguishable. And it matters a lot because there are many sensitive sectors like government and medical sector that wouldn't like to share their data, but we can push the innovation by generating secure synthetic data. And for that, we use tensor networks, and I'm not going to go into the detail of tensor networks here, but there will be a masterclass almost right after this talk that I will dive a bit deeper there. And we use tensor networks which were developed in condensed matter physics to tackle this cursor dimensionality for the many-body quantum wave function. But here we can use it to generate synthetic data. And we use matrix product state, the most efficient and simplest form of them, that is actually very natural for training categorical data, because they're spin models. And then we also like generalize them for categorical data. So they are obviously very good to predict or estimate probabilities for high-order correlation data. And they are also very explainable. We can like directly calculate the conditional density from matrix product state. And then, in order to have this additional layer of differential privacy, we just inject calibrated noise during our training to make the data more secure, differentially more secure. And I just show you quickly our results. So this work has been done in collaboration with multiverse computing. And here we have used like 9 fidelity matrices and 4 machine learning models to assess the performance of the synthesized data for classification. So our development, our models are the blue cross, and as you see, they consistently outperform the state of the art. But one might say, not always like a lot more, but they still do that. But the real magic is when we inject noise and we add the layer of differential privacy, because all the other methods fail. They are not stable when we inject noise. And we need to benchmark against another model, which is called pre-Bayes. And here we have injected 2 different noises, like Laplacian and Gaussian. And as you can see, red and blue crosses are our results, and they are by far better, more than 15% of improvement on all the matrices. And that's basically pushing the state of the art. For some reason, I put the archive link here. but you can ask me for the preprint that we have to have more details. And then for the same data set, we use a quantum circuit board machine to synthesize data. So I jumped through this slide because I just want to discuss the main challenge that we had there. That's basically very basic, but it's very important to overcome these challenges when we do machine learning with quantum computers. So there is this limitation of binary representation of number, because we need to learn the numbers, and then we need to represent them in binaries. Just suppose we have 7 and 8, sorry. And they're represented by like 0, 1, 1, 1, and 1, 0, 0. And each qubit represents one of the bits. And then you need to have like correlation between all these bits, which makes it very tedious for the convergence. And we needed to fix this by inventing a new bit map, which is nearest neighbor kind. And we just map the closed number to closed bit string, like we represent 7 by 0, 1, 1, 0, and 8 with 1, 1, 1, and 0. And that has been already a lot of technical work to come up with this and implement that. But the improvement is reasonably high, 12% faster in convergence time and 20% improvement in the loss function and also in the final outcome of the model. And then I quickly go to the next use case, which is fraud detection. Again, we use quantum-inspired solution for developing prototypes that are almost ready to go to the production. And for this, we choose like a blockchain network to detect fraudulent or potentially fraudulent transaction in real time. And what we use there, because they're represented also in the data set on graphs, we have this two-stage solution. First, we use convolutional neural networks that pulls embedding over the graph nodes and encapsulates the behavior of neighbors. And then we use quantum boosting classification and train it in the embeddings to learn the unknown classification. And actually, the quantum boosting is done on D-Wave annealer. You can call it quantum, or you can call it digital, or a hybrid. But that's the technology, the hardware technology we use for this. And then in each layer of our convolutional neural net, we use tensor networks to compression the weights. So we compress the weights and reduce the number of parameters and expand the expressiveness of our model while we still capture the correlation between the features, the important ones. But then we perform all sorts of combinations here, different models, and we provide a table of different matrices and scores so that we can see, like, based on our use cases, what we want to build, what kind of like AI fraud detection software we want to build. For example, our convolutional neural net tensor network-based ML has the fastest prediction time, while quantum boosting has the best compromise between F2 and the prediction time. It always depends on what you want and what brings you quantum advantage, and that's what matters for the industry. And for the same or similar use case, not the same, fraud detection for credit card, we have worked on a one-class support vector machine solution, which uses projected quantum kernels. So we have benchmarked different hardware platforms also, ion trap and superconducting, and also leverage the partial state tomography to obtain like a good approximation for our quantum state and the quantum kernel. And also we have done a thorough analysis of both like platforms, trapped ion and superconducting platform, based on their hardware efficient feature maps over a wide range of anomalies, and provided like these tables of this F1 matrix for train and test set. But I mean, there is like a thorough analysis in this preprint, but also the main take-home message for us was that we have like plausible evidences that with a high probability our quantum support vector machine solution beats the classical one when the data set is smaller and there is a high anomaly regime. And it also, like, this enhancement is robust to hardware noise and finite sampling. And by this, I slowly close my talk by acknowledging all the people who have done the work with me, and we did it together. So we luckily and beautifully have a flat hierarchy in Bundesdruckerei, and everybody just works together, and it's the same with our partners. And I also thank you all for your attention to come early in the morning, kind of, to this talk. Yeah.